Okay, in this video, we'll start with confidence intervals. And the first confidence interval we'll talk about is a confidence interval for the population mean, mu, when we know the population standard deviations. So some requirements for a confidence interval. First of all, we have to have a simple random sample. Any size simple random sample will do. Second requirement is we either have to have a normal population or a large sample size. Using the guidelines I prefer, if you have a normal population, any sample size will do. If you have skew, then you need at least 15. So that's my skew, or S here. If you have outliers, then you need at least 40. And if you have extreme values, you need at least 100. Depending on what book or whatever you're using for another resource, you might just see some books say for large N, just they don't make a distinction between skew, outliers, and extreme values. They'll just say at least 30. I prefer my way, but that's just another thing you can keep in mind. Okay, and you have to have the population standard deviation. Let's note right off the start, this is a pretty rare case that you would know the population standard deviation. After all, to know it, you would have had to have known the population mean. So it's rare, really not used in practice that much, but it's a good place to start for developing the theory since we already have normal population and z-values and things that we already know about. Some of that will change in later lectures. Okay, so here are a generic or general formula for a confidence interval. At the broadest level, it's just a statistic plus or minus a margin of error. You've seen that plenty of times when you see political polls. When they say someone is in a dead heat or within the margin of error, this is what they mean. They've computed a statistic and added and subtracted some margin of error. And in those things, we're not doing a proportion right now, but if the margin of error, if we were looking at a two-candidate race, if one candidate had, let's say, 54% of the vote, but there was a 6% margin of error, then it's 54 plus or minus 6%. They could be getting as low as 48. Anyway, more on that later. That's the most generic formula. In terms of computations, it's probably a little bit better to think of it in the next way. The statistic plus or minus the confidence coefficient times the standard error. So that confidence coefficient in this lecture will be a z-value, just like we've been doing with the normal distribution and all the way back to the empirical rule. It will be a z-value. In at least a couple of other cases, it will be a related value called a t, but for now, that's just a z-value. And our standard error will be the population standard deviation divided by the square root of n. I think it's really important that you take the time to just really think about this formula and actually just kind of burn it in. We're going to use this same formula or this same generic formula over and over again. So you'll be seeing this many times over the next few weeks. Okay, so there it is. The statistic, x bar, plus or minus the confidence coefficient, which is z, times the standard error, which is sigma divided by the square root of n. Okay, some common z-values for some common z-values for confidence intervals. For a 90% confidence interval, you'll use a z of 1.645. For a 95%, you'll use 1.96. For 98%, 2.326. 99%, 2.576. For now, it's probably a pretty good idea for you just to write those down. We'll have, in another week or so, a different way to get these. We'll get the same numbers. We'll just have a table that has those and a bunch of other numbers on them. But at least for the short run, for the next couple of lectures, these values will be commonly used, and you got to just write them down. Okay, so we'll start with an example. We have a simple random sample of 50 movies. So we have a simple random sample. That's one condition met. The average length of the movie is 118 minutes. The population standard deviation is 14. That was one of the other ones. We had a population standard deviation. And we want to construct a 95% confidence interval. So the other one was that we have a normal population, or we don't have a normal population, but it does, or at least it doesn't say, so we can't really assume that. We have a sample size of 50. That means that skew is okay, outliers are okay because we're greater than 40. So what we need to keep in mind is that this analysis will work unless we have extreme values, because we don't have a sample size of at least 100. If you have the 50 values, and in regular practice you would, you ought to draw a box plot to see if it has any extreme values in it. If it doesn't, then you're good to go. If it does, then the interval that we're constructing in here is not valid. So here I've just written down some of the key information from the problem, that we have a 95% interval, n is 50, x bar is 118, and sigma, the population standard deviation, is 14. Get in the habit of writing down the information from the problem. This one's a pretty simple one, but as the problems get a little more complicated or involved, you really want to make sure you write down the information from the problem. It'll just make everything go a lot easier. So x bar plus or minus z times sigma divided by the square root of n. Just plug them in. 118 plus or minus 1.96. If you wrote down those values from a minute ago, for 95%, z is 1.96. 14 divided by the square root of 50, and that calculates out to be 114.12 to 121.88. So we're 95% confident that the true population mean is in the interval 114 to 114.12 to 121.88. Okay, so can we be confident on the basis of this interval that the population mean is less than 125? The answer is yes, because the entire interval is less than 125. All of the values in the interval are less than 125. Therefore, we can conclude or be confident that the population mean is indeed less than 125. Can we be confident that the population mean is greater than 115? And the answer is no, because the interval includes 115. Not all the value, or you could say not all the values in the interval are greater than 115. It goes down to 114.12. So it probably would have been better if I'd put, can we be 95% confident that the population mean is greater than 115? And the same in the above one. Can we be 95%? Would have probably been better to have those things in there. But just make sure that you look at the entire interval when you go to answer these questions. Okay, so I'm going to go just a little bit more theory on you here. When we construct an interval like this, the interval will include the true parameter, in this case the population mean, 95% of the time. Just as importantly, the interval will not include the true parameter 5% of the time. Now, once we've constructed the interval, it either includes it or not. Our 95 and 5% are statements about a collection of intervals if we were to construct intervals many, many times. Of course, we've only done one. What we know is that 95% of the time we follow this process, we'll end up with an interval that includes the population mean. But we also know 5% of the time we won't. By the way, you'll get a wider interval, but you could move this up to 99% if that 5% error makes you uncomfortable. I would say, however, that 100% interval is probably pretty much useless. I'll give you an example. Suppose that I said the grade point average, I wanted to do a grade point average for students in my class. If I gave you an interval and said it was 2 plus or minus 2, that is a 100% confidence interval because it's all of the range of values. But a much more meaningful statement would be to say that the 95% confidence interval is, let's say, 2.6 to 2.8 or something like that. That's a much more meaningful statement, even though you've given up some confidence to get some precision there. So now we get down to, is the interval we constructed one of the 95% of the intervals that include the population mean, or one of the 5% that do not? And the answer is, we don't know. And you never can. It either is, all we know is that if we did the process over and over again, 95% of intervals would include the population mean, and 5% wouldn't. By the way, I'm making another video that will really stress this point and show it graphically. So you can go ahead and take notes now, but if you don't quite get it, I think watching that video will help out. Okay, so example 2. We have a simple random sample. Okay, that's good. Of 30 students. Now we'll have to wonder whether or not that's large enough, since I can go ahead and tell you this isn't going to say you have a normal population. But anyway, the average time is 43 minutes, and the population standard deviation is 10, and we want a 98% confidence interval for the population mean time to complete the exam. Again, first thing is write down the information from the problem. And my question is n large enough? We don't have a normal population, and we are using that 15, 40, 100 rule back from the central limit theorem. So what you should do, you have those 30 values, make some graphs. So let's say here are some different options here. Remember, our n is 30. So my first set of graphs there, A, is 30 large enough? And the answer is yes. There aren't any outliers. It looks like there is some skew, but there aren't any outliers or extreme values. And so 30 is large enough. In B, the answer is no, 30 isn't large enough because there's an outlier. And the answer on C would be no. There's an extreme value there. So you have to have at least 100. 30 is not at least 100. And the bottom one there looks like a normally shaped distribution and without even any skews. So that's okay. So yes, skew's okay when you have 30. No, outliers are not okay. No, extreme values are not okay. And yes, a small sample will do when you have a normal population. And our evidence suggests that we're on track with that. Okay, so here's my interval. Again, I've repeated the information. X bar plus or minus the confidence coefficient, which is z, times the standard error, which is sigma divided by the square root of n. Plug the numbers in and calculate. And that's all for this video.